Hello, and welcome to Lesson 4. Lesson 4 is the quotient rule, when I have a function divided by a function. So now we're going to take a look at how that works, compare it to product rule, which we've already compared to power rule. And let's get started. Let's just, for example, think about what we set up before with function f and function g, but now I'm going to set up a quotient of function f and g instead of a product. If I want to take the derivative, let me not put a y on that, let me just put a d. If I want to take the derivative with respect to x of that quotient, what it is the derivative of the top, f prime x means the derivative of f, times the bottom, but now it's minus. Since the product and quotient are inverse operators, it makes sense that the product was plus, so the quotient is minus inverse operators. So just like the product rule, it was top, first, and second, we're going top and bottom. So the derivative of the top times the bottom minus the derivative of the bottom times the top. So it's very much like the product rule, except that's not all. We have to then divide the whole thing by the bottom squared. So whatever that function is, I'm going to square it. All right, so it's very similar to the product rule, but slightly different as we have a quotient answer for the quotient rule. All right, so if you look at this, all right, I want to make a little observation before we go on and test this rule. And the observation I want to make is this could be written f of x over g of x could be written as a product f of x times 1 over g of x, right? It could be. That's basically the inverse of g, right? Or the reciprocal of g, let's say. That's probably a better way to say it. So what that means is I could, in theory, convert a quotient rule to a product rule if I wanted to, because I can convert a quotient to a product. So what we're going to do is do the quotient rule with a function and then check it by converting it to a product and doing the product rule and seeing if that actually does verify our quotient rule for that one and only one example. So let's do one. Let's do 2x plus 1 over 3x squared. Let's keep it simple. And I'm going to do the derivative of that, okay, with respect to x. And I'm going to go ahead and write my rule in its form. The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Very important, okay? And let's go ahead and apply that. Let's just do that first, and then we'll test it the other way to verify it. So the derivative of the top. The derivative of the top, it's 2x, x to the 1. 1 times 2 is 1. 1 minus 1 is 0. So it's going to be 2x to the 0, or it's just going to be 2 plus the derivative of any constant is 0. So the derivative of the top is just 2. Bang. That's the derivative of the top. What's the bottom? It's still 3x squared. We haven't changed a thing. Now the algorithm says minus. Minus what? Minus the derivative of the bottom. So let's do that now. 2 times 3 is 6. 6x to the 2 minus 1 is 1. I'm not going to write that 1 now, because we're getting far enough along, you should be able to handle that. So that's the derivative of the bottom times the top. What's the top? Well, it's still 2x plus 1. Nothing's changed. All over the bottom squared. Well, that's 3x squared all squared. It's not 3x squared, x squared. It's 3 squared, x squared squared. Everything in there is squared. It's not distribution. It's the power of a power. It's your exponential rules again. Okay? So don't let those, mess you up. Okay? So here we go. So when we're doing this, we can say, fine, let's simplify this bad boy out, because if we're going to compare it to the other version, let's get a simplest form equivalent. So let's do that. Let's look at it. So I can see that these are just two monomials, really a constant and a monomial. But this negative 6, not just 6x, it's negative 6x, must distribute to both of those pieces. And this square squares everything in there. So let's see how that looks. That turns into 2 times 3, or 6x squared. That's pretty straightforward. Okay? But what about this part? Negative 6 times 2 is negative 12. X times x is x squared. Negative 6x times 1 is negative 6x. That's my distribution. 3 squared is 9. X squared squared is x squared times itself. X squared times x squared is x to the 4th. Okay? And hopefully you notice that there are like terms that can combine. And when I combine them, I get 6 minus 12 is negative. So negative 6x squared minus 6x all over 9x to the 4th. Okay? Something should be jumping out at you now. Take a minute, see if you can simplify. Okay, welcome back. Hopefully you saw the common elements in all terms, but I'm going to go ahead and break them into prime factors to help you see it. So 6 is 3 times 2, and x squared is x times x. However, this is a negative 6, so I'm going to put my negative with the 3. It would have went with the 2 if it was in front. It doesn't matter. It's got to be with one of them. Okay? Let's look at the next one. Again, 6 is 3 times 2, and x is just x, and one of those has to be negative. And then below, 9 is 3 times 3, and x to the 4th is x times x times x times x. Okay? So what I've done is I've given myself a thinking graphic that I can analyze with. I don't always have to do this, but mentally I'm doing this. I'm thinking about what is common. So let's start. There's a 3 and a 3 and a 3. Now, not necessarily the negative sign. I'm just circling the 3. Negative is still there. And I keep looking. There's a 2, but there's not a 2 there. So guess what? My last number was 3. That's it. That's all there is. It's all they have in common. They each have a 3 in common. So if I'm going to have that top and bottom, I'm going to go ahead and express it top and bottom. Next, I continue. Well, 2's would work, so let's try x's. There's an x, there's an x, there's an x. Great. There's an x in common, right? And I keep looking. There's a second x. There's not a second x. Even though there's more x's everywhere but there, that's it. This is the limiting condition if you think about your chemistry. I have two constituents to make a compound. If I have more of one than the other, the one that is the least amount limits how much compound I could get. I could have other constituents left over, but if I can't partner them, I don't get a compound, right? It's the same kind of thing. I had more x's and everything but here, so this was my limiting condition. In fact, these two were limiting for 3, but this was limiting for x. So you could get kind of nuanced about it. But the point is they each have a 3x in common. So what is left over is what they don't have in common. Now, why did I write it this way? Just so you could see that that's 3x over itself, isn't it? Which is just really 1, and 1 times anything is that thing. And so the 3 and the x don't disappear. They cancel. They cancel and become a 1. I don't have to rewrite it. What's left uncircled is my simplified fraction. So from now on, I don't have to write that out in front, but I just want you to understand why it's disappearing. It isn't magic, right? It's not magic. It's that this is a product, and that's a division, and division undoes multiplication. I can divide those away. So what's left in this term is what's left here, negative 2x. And what's left over here is negative 2. And what's left down here is 3 times x times x times x, or 3x to the 3rd. that's actually, if I extend my page down, that's my simplified answer. I could factor the negative out in front, and that would be negative fraction 2x plus 2 over, but let's just leave it alone. Let's just say I have negative 2x minus 2 over 3x cubed, and that's my final answer. Again, that could be written as the opposite of 2x plus 2, right? That could be up top or next to the fraction bar. Those are equivalent, right? Those are equivalent. Again, I just factored the common negative out in front, and those became positive as a result. You got to be able to do that, okay? Not that concerned about that right now, but this form is what we're going to look at. Okay, to help me get this, all right, I'm going to go ahead and go up here, and I'm going to erase I'm not going to do that even. I'm going to go ahead and drop down so I can clone that. And now I'll erase it. So now I'm going to erase all this piece here. That way it's still on the other page if I want to go back to it for the lesson. See the answer's still down there? Okay. So now I'm going to go back up to full screen. All right. Now I want to go ahead and I'm going to write this as 2x plus 1 times 1 over 3x squared, and I want to do the derivative with respect to x of that. Now it's a product. Remember, I'm saying this function times 1 over, f of x times 1 over g of x. f of x times 1 over g of x. f of x divided by g of x is like f of x times the reciprocal of g of x, which is flipping it upside down. All right, so now you see that I have that. This becomes an issue I don't want to contend with. That x could be better served up there. So this could be better written as 2x plus 1 times 1/3. I don't want to flip the 3 up because the 3 is a number and it can be on the bottom just fine. But the x squared can come up and be x to the negative 2. Now I can do my power rule without trying to do some mental gymnastics that'll only end up getting me confused and making a mistake. All right? Notice, could I just distribute, boom, boom, and go? Probably looks like I could, right? Let's just, though, remember we already showed that I could turn a product into a polynomial and it would work. We did that. So we showed the product rule is the power rule if I do the product first. So let's accept that, and now let's go ahead and say, well, is the quotient rule indeed a product rule? If I convert it and do it as a product rule, I should get the same answer, equivalency. Let's test that. So in testing that, we're going to call this the first and this the second. So it's no longer top and bottom, is it? Now it's first and second. And remember the product rule? The product rule was derivative of the first times the second plus derivative of the second times the first. That's what we're going to do now. We're going to do the product rule. So the derivative of the first, 2x plus 1. We've already done that, right? 2x becomes 2, 1 becomes 0. So the derivative of the first is 2. The second is 1/3 x to the negative 2. It is what it is. Then plus, because that's the algorithm. In this case, the algorithm takes the place of the difference quotient, which is a nightmare when you start trying to do these complicated problems. That's why these rules are so cool. So next is the derivative of the second. Well, negative 2 times 1/3 is negative 2/3, yes? And then negative 2 minus 1 is x to the negative 3. So that's the power rule, because that's just a single monomial term. That's the derivative of the second times the first. The first was just 2x plus 1. Okay? So now it's done, but it doesn't look like my other piece looks. So I want to go ahead and put everything back, get everything out of the negative exponents, distribute, combine, do everything I can to simplify it into an answer fraction. Or we expect it to be a fraction, or whatever answer it is. So this is going to rewrite as, well, I can do 2 times 1/3, can't I? That's 2/3. What's going to happen is this x to the negative 2 is going to go to the bottom, so that's going to be 2 over 3x squared. That's really what that's going to be. Do you see that? I hope you can. All right. Now, I'm going to say plus for now, but I'm going to go ahead and I'm going to do some distribution. But to distribute here, this bad boy is going to come back down there as x to the third, right? So I'm not thinking of it up there. I'm thinking of it as the bottom. So what's 2 times negative 2? Well, that's negative 4. And the x is on top. On bottom is 3x cubed, right? That's the first term. The second term is 1 times that term. That term is negative 2 over 3x cubed. So negative 2 over 3x cubed is the second term. Now, since this is a plus, when I distribute it through, it doesn't change the signs, does it? So let's go ahead and take and make that minus and minus. Okay? By combining these terms, right? So the thing I have now is almost ready to combine. I almost have a common denominator. And I could break this apart 3 times x times x, 3 times x times x times x, 3 times x times x times x. Hey, the only thing missing over here is one of the x's. And these two are good as is, right? Because a 3 goes into 3 and x squared goes into x cubed, but there's an x missing. So what that means is I'm going to need to do x times x over x to get that to all be a common denominator, 3x cubed. Yes? And now I can do my math. 2 times x is my new numerator there. Minus 4x, I like that, minus 2. Right? And I notice that, hey, I like that because they can go together. That's the reason I like it. So 2x minus 4x is negative 2x. And negative 2 is all alone on the end. And 3x cubed is the common denominator. And when I look down, I see that negative 2x minus 2 over 3x cubed is indeed an equivalent form. Thus proving that the quotient rule could be written as a product rule, which we've already proved could be written as the power rule if I do the product first. Therefore, all of these are verified. In a specific instance, you could do it generally, but it would be tedious for me to do for you. Let's do a couple of other ones before we end this lesson, because that's it. That's the quotient rule. These rules are simplifying the difference quotient that would be otherwise a disaster and making them more understandable and easy to apply. So let's do another one. Let's do the derivative of, let's really be ambitious. 3, well, I don't want 3 squared, that's silly. 3x squared minus 2x plus 1 over 4x cubed plus x. Yeah, let's just do that. So that's a big function, and it could be much bigger. But as you can see, when I start to do simplifications and all that and put them together and square, it can be crazy. So we're going to write the answer, again, like we did with the product rule, in its first step form. Okay? So that we can check it. But then you want to simplify. Seeing the actions that we did simplifying shows you that that's a skill you need to really understand. All right? But to make sure you're getting the derivative, I'm just going to check the derivative process. So the derivative process is derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared, right? So let's do that. Derivative of the top. It's a polynomial, isn't it? So I can do the derivative of each rule, each monomial as a power rule. That's what I'm doing. So 2 times 3 is 6x to the 1. 6x to the 1. I don't need to show the 1. Next, 1 times negative 2 is negative 2x to the 0. So that's negative 2. And the derivative of a constant goes to 0. So that's the derivative of the top. Times the bottom. Bottom is 4x cubed plus x. Then I want to do minus, because that's the algorithm. The derivative of the bottom. Well, 3 times 4 is 12. 12x to the 2, because I take one away, right, when I'm doing the power rule. Plus x to the 1 is 1 times 1, x to the 0, so that's 1 x to the 0, or 1. Now, if I just did that, I'm going to be wrong. So I want you, when you're doing this, to always, after you write that minus, put a parenthesis there, to remind you that that's minus the whole thing there, not just the first term of it. Very important distinction. So that's the derivative of the bottom times the top, which is all that gobbledygook. Now you can see, boy, if we were expanding that, we would have a lot on our plate. Okay? Am I done? Almost. All over the bottom squared. How do I write that? Here's how. I write the bottom thing. I can close it with symbols of enclosure, and I put a square. That's how I write it. It's done. All right? That's completed. Now, if I wanted to simplify that, that's a whole other story. That's something you can do on your own. But clearly, I'm going to distribute. I'm going to have 4 terms at least that might combine. Here, I'm going to have 2 times 3. I'm going to have 6 terms that might combine. Here, I'm going to have 4 terms that might combine. Then after they all combine, something might factor out and cancel, and I might end up with a simplified form that looks drastically easy or simpler, or maybe just not quite as convoluted, but not that simple either. That's for you to decide, you to figure out. Okay? Let's do one more. X to the third minus 5/9 x squared plus 2x all over 17/5 x to the third plus 16x minus 4. All right, ugly numbers. Much more realistic. Decimals would have been the most realistic form. So let's go ahead and do that. Derivative of the top. 3 times 13 is 39. 3 minus 1 is 2. So that's 39x squared. Okay? The second one, 2 times 5/9. Well, that's 2. 2 over 1. So 2 times 5 is 10. 2 times 5/9 is 10/9. 2 times 5/9 is 10/9. Okay? I have double the amount. So almost a little more than half, and then a little more than a whole when I double it. So 2 times 5/9 is 10/9. The opposite positive is negative. And then 2 minus 1 is 1. So that's 10/9 x plus 1 times 2 is 2. X to the 0. So there's my derivative of the top. A lot of stuff, right? A lot of stuff. Times the bottom. You know what I want to do here? This is so much stuff. I want to make it a little smaller so it fits on the screen. Okay? So that's times the bottom. 17/5 x cubed plus 16x minus 4. Minus, because that's the algorithm, right? Derivative of the bottom. 3 times 17x, well, it's 3 times 17 over 5. So 17 is 2 less than 15, right? And so if I take 3 15s, that's 15, 30, 45. But I had 2 for every 17, so 2 times 3 is 6. So 45 and 6 make what? 51. That's kind of the Common Core approach, right? Grouping numbers. But I can say 3 times 7 is 21, carry the 2. 3 times 1 plus 2 is 5, and it's still 51/5, right? 51, oh, what did I forget? When I put that minus, I got to put a parenthesis. Let's never forget that. So that's 51/5 of x to the 3 minus 1 is 2, so x squared, right? 1 times 16, that's 16x to the 0, and that becomes 0, right? times the top, which I think I can fit in there. 13x cubed minus 5 over 9x squared plus 2x, thankfully. All over the bottom squared. What is the bottom? It's that. 17 fifths x cubed plus 16x minus 4. Symbols of enclosure, squared. Again, in calculus, the answer is longer than the question sometimes. Here's an example. This is one to simplify. If I simplified this, what I would do is I would distribute that negative through and make this a plus. That way I could just combine stuff easier. But that's up to you. That's a goal that you can chase. All right. The quotient rule. That is the end of the lesson.